So. The part that you're gonna think is terrible to start with. Which ends up turning out to be not too bad once you actually do it. Is derivatives of trig functions. So this is 2.5 and we're doing derivatives of trigonometric functions. Trigonometric functions. That's a mouthful to say and spell. So, to do it, we're gonna go back to limit laws. Just to show where they come from. Once you know the answer from the limit laws, you don't need to do the limit laws anymore for this. Let's start with, we're gonna start with taking the derivative of sine x. This is the limit as h goes to 0. Sine of x plus h minus sine of x all over h. Remember, we got f of x plus h minus f of x over h. And limit as h goes to 0. That's what we're applying here. And you're like, what the fuck do we do with sine of x plus h? Anybody know? Anybody remember? Hopefully you all know. Not everyone's going to, because not everyone had to trig in high school. We can do something with the x plus h. Does anyone remember what?
The difference,
You're close, wrong word, some formula. We know them as a sum and difference formula. If we had sine of a plus b. This is sine a cosine b
right here,
plus sine b cosine a.
the difference I did.
There you go. So we're gonna apply that here where this is x and this is h. So this becomes the limit. As h goes to 0. We have sine of x cosine h plus sine of h cosine x. That's the part we changed. And then the parts we didn't change were the minus sine x and then over h. Okay, so two of these have a sine x in them, right? Let's split those off and make them one limit. We'll have sine x cosine h minus sine x over h. And then I'm gonna do plus limit as h goes to 0. Sine h cosine x over h. And we can factor out sine x on the first one. And on the second limit, cosine x doesn't have an h in it. So I can actually pull the cosine x out. And we'll make this limit as h goes to 0, sine h over h.
Did you see we pulled it out?
Cause it does not have an H in it. So it's considered a constant in terms of things that have H's. And it's multiplied by what's there. We can actually do that over here too, now with the sin x, we can pull the sin x out. Now what?
Sign the breaks.
Sin of h over h is one. We did that the other, well, limit as h goes to 0, sin of h over h is one. What about the other one? Question. What is it? 0? Good memory. So I got 0 times sin x. Plus 1 times cosine x. That's gonna be the derivative of sin x. That's what we started with. So we've got the derivative of sin x as we clean that all up. Is just cosine x. Boom. That doesn't seem too hard to remember, does it? Derivative of one trig function, major trig function is the other major trig function. Like sine and cosine are the two most commonly used trig functions because they compose everything else. Let's find the derivative of cosine doing something similar. Those of you that want to start working ahead on your own while others are still writing down your notes. I'll put it up. And just to get you started, put in what we got. And I'll even write down the cosine sum formula. The cosine sum formula is the one that cosine switches signs. The sum has a minus sign and the difference has a plus sign in it. You're done. Let me give you a few minutes to work that out, see if you can figure it out. It does very similar to what we did in the last one. you've done it right, you're gonna get negative sine of x, we'll walk through it in a second, but.
When is sine of h over h equal to 1? When it goes to 0?
We did the squeeze theorem on it, it's been a while, it was in like chapter 1. Hopefully you have it in your notes, otherwise you weren't taking notes that day. For now, just memorize it as one, as soon as we learn L'Hopital's rule, you don't need it anymore. Like, I'll be honest, when I came back to school and started teaching, it'd been so long since I'd seen sine of h over h was one that I didn't remember, but so I immediately started using the L'Hopital's rule. You're gonna like L'Hopital's. And like, they're like, we don't know how to do that yet. I'm like, I don't know how if I can tell you this is one then. I wasn't teaching the class, I was tutoring. And they pulled out their notes and showed me the squeeze theorem, I'm like, oh, okay. And top one yet. Give you another 3 minutes, then we'll do it together.
Or.
And I don't know that you'll see the squeeze theorem again until the later part of calculus 2. Like, or need it. Can't recall us ever needing it again in calc 1. But in calc 2, you'll use it for convergence theorems. And if you ever, well, when you transfer, if you take a real analysis math course, if you're a psychopath and become a math major like me, you have a squeeze theorem left and right.
Comes after the differential equations for that class.
That is the last class in the sequence here at COS. There are other. There's like numerical analysis you can do where you start breaking it down into how you do harder stuff that you can't do by hand. You tend to need a computer for it. There's other complex. Like you learn about, complex numbers. There's a whole shitload, you can take a whole class on complex analysis, what it's good for and stuff like that. Other applications of math, and then
Does a discrete math fall into that, or is that a computer science thing?
discrete math is more a computer science thing. Because I mean, it's effectively just working with whole numbers. So like. You learn how to work with whole numbers in fucking first and second grade. But it's like, where's the application, like doing more with it is in applying it to computers. If you're enjoying math classes, I encourage you, when you transfer, take other math classes too. You'll find like numerical analysis, if the school you transfer to has it, you'll see how to apply this shit to cutting edge problems. Shit that you can't take the derivative of, or stuff like. In calc 3, we start working with multiple variables. And when you go like into differential equations and stuff like that, you start to. Not only with our real world is in 3 dimensions. Here, we're doing 1-dimensional calculus, so we've only got one variable, it's like going in a straight line. We tend to graph it using y equals something like that, but it's still not 3D, y and x is just 2D. When we go 3D, we have X, Y, Z, but that's calc 3, and then when you do like differentials and stuff like that. Now you throw in time and. Like the fourth dimension, we often call time the fourth dimension. And there's a lot you can do there, and since. Doing calculus in 3 dimensions and tracking how it changes. Every second, like you would try to figure out doing like an experimental thing. Is a lot more than the human hand can do, so that's where the computer shit comes in. It's kind of neat. But numerical analysis starts you with like just doing this same shit, but computerizing it and kicking it up a notch. And then like grad school, you do like 3D with computers and stuff. Alright. Let's take a look at this, let's apply that. Dx cosine x equals the limit as h goes to 0. We've got cosine x cosine h. Minus sine x sine h. And then I've got minus cosine x. All over h. Two of these have a cosine x in them, we'll put those together. H minus cosine x over h. And that leaves us with a minus, limit as h goes to 0. Sine x sine h over h. Again, x is not h, so anything that's just an x, if we can factor out of everything, we can factor it outside. Both of these have a cosine x, we can factor it out and put it outside. Cosine h minus 1 over h. Then same thing here, we can factor out the sine x. That was 0 and that was 1. Dx of cosine x is negative sine x. Very similar to the sine x one. So derivative of sine is cosine. And derivative of cosine has a sign, you just gotta remember which one turns negative. That's the only real trick thing to remember. Let's take a 10-minute break. When we get back, we'll do tangent x.
Yeah, isn't
What?
sine of h over h equal 1?
Just making sure.
Yeah, 1, sorry.
Just kind of looking at like
Okay, wait a second.
Thank you. And if you wanna try this earlier, don't do limit loss. Do quotient rule. Let me pause. Alright, so this is. Derivative of sine x over cosine x. So high is sine x, low is cosine x. So d high is cosine x. And d low is negative sine x, using what we just learned from the last 2 problems. And remember, when we do quotient rule, it's high prime low minus high low prime over low squared. We have ddx of tangent x equals high prime, which is cosine x. Times low, which is cosine x. And then I have minus high, so minus, and then high is sine x. And then low, derivative of low is negative sine x. All over low squared is cosine squared x. So clean that up a little bit. We have cosine squared x for the first part. And then I have minus minus is a plus. Sine x times sine x is sine squared x. Over cosine squared x. What's the top equal? Equals 1, right? And if you don't notice it right away, this is 1 over cosine x squared. But that's secant x. And since it's squared, we have secant squared x. Derivative of tangent x is secant squared x. That's 3 of our 6 trig functions. We're gonna just write down a list of the 6. If you want to challenge yourself at home, derive the formulas for the other 3. But let's write down our trig list. So, derivative of sine x is cosine x. And derivative of cosine x is negative sine x. And we just saw the derivative of tangent x is secant squared x. Now, the one that goes with sine x is cosecant x. It is not just 1 over. It is negative cosecant x cotangent x. And the derivative of secant x is secant x tangent x. Finally, the derivative of tangent x. Just like, or not tangent x, we already did tangent x, cotangent x. Just like tangent x led to secant squared. This one leads to cosecant squared. But it's negative. If you want to challenge yourself, derive these at home. You're just gonna need to memorize these three. Well, it's helpful to memorize them all. The way I remember the different, what goes with these two. I remember cosecant and secant have themselves in the derivative. And then I know they either have a tangent or cotangent with them. The way I remember it is the cosecant one, everything starts with C. And like the derivative of the C one, it has a negative. In fact, you'll notice all the ones that have to take the derivative of a trig function that starts with C have a negative in it. Coincidence. I think, I don't think they named them after they learned derivatives. Just turns out that way. And the way I remember cotangent is it's just like tangent, but it uses the other. Weird trig function. In my head, secant and cosecant are weird trig functions. Although secant is much less weird, cosecant is the weird one, weirdest one. It just doesn't pop up that much. We don't use cotangent and we don't use cosecant all that much. You guys ready for some fun with all this? As if you haven't been having fun yet. Find the derivative. F of x equals x squared cosine x. This is gonna have to combine some shit. This one has product rule and trig functions. All these little things we're doing in chapter 2 with the derivatives, not necessarily with the limit stuff, but with the derivatives. They are literally the basis for everything in Calc 1, 2, and 3. Well, we're gonna learn integration, which is doing derivatives backwards. But like if you know the derivatives, you can just work backwards. Learn like fucking flashcard, whatever you get, it takes, burn this shit in your head. This and chain rule. And then when we do L'Hopital's rule, those are like pretty much what you need for almost all of calculus. Can't recommend flashcards enough. They work, they really do. So then we gotta take a dump, gonna be in there a while. Flashcard the shit out of it. So if I do the derivative on this, I have two things multiplied together, it's product. We can do the derivative of the first set times the second. Plus leave the first one alone and then do the derivative of the second. So the derivative of x squared is what? It's 2x, and we leave the cosine x alone. And then we leave x squared alone, and what's the derivative of cosine x? Negative sine x. So we should probably deal with that minus sign. We can write it as 2x cosine x minus x squared sine x.
Is that the final answer?
Yeah,
Oh, well, I was trying to like make it even simpler.
I guess you could factor out an x, but I don't know that.
Yeah,
makes it
okay, that's
simpler.
what I was kind of like figuring out.
Just letting everybody finish writing. If you're ready to start on the next, as I suspect some of you are. Take the derivative of g of x. If g of x is the square root of x times secant x plus 3. Next week, on Tuesday, we're doing 2.6, which is on the chain rule. On Thursday, we're going to do a group practice test. I will put up a practice test on campus this weekend. Probably tomorrow. Try to do it individually before you get here, that way you can like figure out what you don't know and do know and. Makes your group time better. The only thing you won't be able to do this weekend is the chain rule one, which is 2.6, and I'll label which ones are those. I'm trying something new. Presumably, I've heard from no one here at COS, but other schools doing group tests has helped raise grades, and I want you guys to succeed. So we're gonna give it a try and see how it works out. If anything, it gives you extra practice talking with people that is not your instructor. Which is sometimes easier. Some people don't have a problem coming up and asking me questions, but others. Wouldn't ask me a question to save their fucking life, like if they were, maybe if they were drowning, but. I swear you're still there?
Yes, I'm here. I'm here.
Are my practice tests a fair example of what they can expect to see on a regular test?
Why they can expect to see in a regular test?
If with a practice test, when they take a practice test, can they expect something similar on the regular test?
Yeah, it's pretty similar.
Some teachers like, for fucking some reason, give you all the review and practice for shit that doesn't show up on the test, which is.
Yeah,
Fucking asinine, if you ask me, that doesn't help students at all. So
Yeah.
what you're gonna see on your practice test, you'll see similar questions. I don't,
yeah. You changed almost. You are just gonna change the number almost. Yeah.
for the most part,
Yes,
some of them it is just changing numbers, sometimes it's adding a little bit more or less, but it's the same ideas.
I had a terrible chemistry teacher, and she was like, for practice, do these problems, and when you see at the test, it was completely different. Almost all the class was complaining, and that's the only class I got a B. I have A's in all my classes, and in that terrible teacher, I got only a B for that class.
That's braggart.
I hate it.
Yeah, hey, I don't get practice tests that, why give a practice test if it's not having anything to do with the real test? Why would I ask you to waste your time practicing something that I know isn't gonna help you on the next test? Doesn't seem smart. Alright, so like probably the best way of going about this is first off, writing that as x to the 1/2. And so when I do d dx of this. I have a product rule. So I'll do the derivative of the first. Times the second, plus leave the first alone. Times the derivative of the second. And then we add the derivative of 3. Just writing out what I'm doing. And using ddx rather than the prime notation now. Just to get you used to seeing it both ways. This is usually written as dg dx. And the derivative of 1/2, x to the 1/2 is we bring the 1/2 down. And this is, we lower it by 1, so 1/2 minus 1. And the secant x stays the same. And then what was the derivative of secant x?
Secant x. Minus. No, times a tan x.
Times tangent x, yep. And what's the derivative of 3?
0.
0. I'm just making a note of it, it's gonna go in the next one. But if I don't put the plus 0, someone will ask me what the fuck happened to the 3. Guarantee you. Alright, so we got dg dx. Is 1/2. This is x to the negative 1/2 when we're done. And that is the same thing as 1/square root of x. So this ends up being 1/2 root x. Times secant x. Plus, I'm gonna go back to the square root notation since that's what we started with. And if you don't like that form, you could put the secant x over the 2. You get it?
You don't have to further simplify.
I was gonna say, could you better secant x, or
We could, but is it gonna help?
not really, but is it, it's just okay to leave it like that?
Yeah. The only thing some teachers might want you to do is rationalize that square root of x. But like, I'm not worried about it. If you got to this point on the test, I'm happy with the answer. All right, let's give you another one. We got to be private roll a couple times with the trig functions. Guess what else we get to do with the trig functions? Find h prime of x if h of x equals cosine x divided by 1 plus sine x. Yeah. Yeah, quotient roll with the trig functions. Good times. Maybe as a reminder, I'll write down over here. ddx of h over L is h prime L minus HL prime over L squared. Like you're trying it, Jacob.
Trying to figure out how you started.
I would start by identifying high and low.
So what I did. Have a high. Why was I thinking that the load, like it always had to be on the top? Like the low can be on the bottom?
Low is the bottom, high over low.
I don't know, I guess.
Would top and bottom work better than high and low? I use high and low because you can.
I don't know, I guess it was
Or
just
short to spell.
when we were first looking at the book rule with having. The way you wrote it out of like low D high minus high D low. And it was like the U's and V's and stuff, I thought it always had like start on top.
No, no,
Was
the
that,
low,
that's how you identified it?
no, yeah. The L is what's on bottom, the bottom part of the fraction,
And you even wrote the H, the high over low part, I still.
but. Yeah, I mean, we just did learn both of these things today. You don't have a whole lot of confidence with either right now. That's the point of even making you guys do this. You want more man, we'll do it again. What's the derivative of the high? Negative sine x. What's the derivative of the low? Just cosine x. So h prime of x. We have high prime. Which is negative sine x. Times low, which is 1 plus sine x. Minus high, which is cosine x. Times low prime, which is cosine x again. All over low squared is gonna be cosine squared. Nope, 1 plus sine x squared. So if we distribute. I've got negative sine x. Minus sine squared x. And we'll put the two cosines together to make cosine squared x. Over 1 plus sine x squared. Those are all negative, I'm gonna factor out the negative. I put it out, the negative outside the fraction, but you can put it on top, put everything in like brackets or parentheses, that's fine. Anything clean up here?
Yeah, sine 2 squared x plus cosine squared x equals 1.
Yeah. So the top condenses down to that. And the bottom, that. Put the negative over there, make it a little bit closer. So what do we end up with for h prime x? Yeah, notice the sine x plus 1 is in a different order, but it does cancel one of the things on bottom. Or you put the negative on top. Both of these answers are equal, the only reason I would recommend the latter. This one. There's no chance. Of mistaking the minus sign as part of the fraction. You know what I mean, when that minus sign is right next to the fucking fraction bar, it looks like the pin ran out of ink for a split second.
You mean the minus sign to be specifically towards the term at the top though?
Yeah, like, they're both right. But like, if you write it like this, you'll notice that it can be easy to fucking go. Is that one fraction? Or you might have meant to do it separate, but you end up getting it so fucking close that it looks like it's part of the fraction bar. And then it doesn't look negative. But if you have the negative on top, that doesn't happen.
Can you go a little bit up? You go. That's fine, thank
Find the fourth derivative of sine x. I'm actually gonna use the ddx notation here. Cosine x. The second derivative looks like that. That's just doing ddx of cosine x. Which is negative sine x. So this is almost like saying y equals sine x. And we get down here and y double prime equals negative y, that's kind of cool. Third derivative. We're doing the derivative of our last step was negative sine x. That's gonna get us negative cosine x. Or y triple prime equals negative y prime.
Which is back at sin x again. Well,
The fourth one, we get back to sine x, don't we? Back to sine x. That's pretty neat. The trig functions go through a loop. That keeps going, the more you keep, you could take the eighth derivative and you're gonna get back to the first. The only reason I'm showing this notation right here is this kind of shit is what you'll see when you start looking at differentials and stuff. You'll see stuff like that, it actually comes up in differentials, we use. The sine x and cosine x are wave functions, if you take, when you take physics or differentials. A lot of that stuff is doing derivative waves and stuff like that. So this notation comes up. One more problem for you. Assume that, assume that position of a particle. On the x-axis. Is given by. X equals 3 cosine t. Plus 4 sine t. Where x is in feet. T is in seconds. Part A, we will find the particle's position at. Equals 0, t equals pi over 2, and t equals pi seconds. So this notation is gonna look a little weird, but I wanna remind you, like, when we do like y equals f of x. We write the ordered pair as xy. So here we've got x is like a function of t. We'll do ordered pairs as tx. Which is, looks weird having x as the second thing. But t is the independent variable, and x is the dependent variable here. And we're just plugging in the times. At t equals 0, x of 0 is 3 cosine 0 plus 4 sine 0. How much is that? It's 3. Cosine 0 is 1. Sine 0 is 0. Bless you. Godzilla. Godzilla sounds like a Zoom type. If you're not religious, that's a way of having the same sentiment without a religious notation. Because in times just bless you in German, so it's not changing anything. Some people are like, I don't want to hear bless you, I'm not religious. I've met atheists that are like that, I'm like, get over it, I'm an atheist too, but like people mean well when they're saying it. X of pi over 2. 3 cosine pi over 2. Plus 4 sine pi over 2. Now the cosine pi over 2 is 0 and the sine of pi over 2 is 1, we just end up with 4. So this is like 0, 3, this looks like pi over 2, 4. Put in pi. Zero and -1, we end up with -4. I'm sorry. I got them backwards, that's -1, that's 0, you get -3. Fuck am I doing? Looking like I don't know my trig values, that's what I'm doing. And on B, find the particle's velocity at the same time. This is basically a dot moves back and forth on the number line, back and forth and shit. What are you doing?
I don't imagine that on a graph. Going. Wait,
So if you were to graph it. X is this axis, T is that axis.
that's why. No. I still looking at it right, goes up and then
0, 3. Pi over 2, 4. Pi -3 is way down here.
goes, just drops.
But if we're just looking at it on the x-axis, the single line x-axis,
Oh, then yeah.
it's going back and forth. So we take the derivative here. What's the derivative of this, what's dx dt here? That's velocity, derivative of position. We have 3 with a negative sine t, so I'll put the negative out front. And then we've got 4 cosine t. We're looking at x prime is 0, x prime pi over 2, and x prime pi.
constant.
I don't wanna use a coordinate pair like that on this, that doesn't make sense.
Well,
It's not a position, it's a velocity, it's half quickly without smoothing.
I is a constant, right?
Yeah. Why would that matter?
No, it's not,
You take, okay, so take the derivative before you put shit in.
Yeah.
You put in pi over 2. We have -3. And at pi. Wait, that should say cosine there. We have -4. So it's it's going up really fast. At 4, then when it gets here, it's starting to go down at -3. And as we get here, it's going down even more at -4. Yeah, it's 10 o'clock. I can't hold you any longer. Get the fuck out. Have a good weekend. I'll have that practice exam up. Try to get your homework and be caught up with chapter 2.5 by class on Tuesday. Cause we're like, you really wanna be like focusing on 2.6 on Tuesday and Wednesday. So that you're actually, when you're coming up to do the practice class on Thursday, you're ready for it.
Yeah, the homework is pretty fast to do, especially if you go so someone help you out.
And I will be at the Mesa Center at 8 to 2 on Saturday.
Okay. I will be there asking only one question, okay?
Okay,
Jones, how did you get the equation in green?
I took the derivative of that equation there
Oh, okay.
with respect to time.
I won't ask more than one. I won't ask more than one question. It will be a only question, but it will be too long question,
Okay,
like 2 hours
that's a long
question.
drive for you to ask a question. Do you have a
Is-
class
is-
tomorrow at 9 a.m.?
No.
Hop on Zoom at 9 a.m. tomorrow. That way you don't have
I'm
to
just
drive
I'm
over.
just kidding. I'm because you say you only ask say I have one